Chris. I'm here to teach you RankNTypes, or higher rank polymorphism. The title should give you some idea of how I feel about them. Who here feels like they understand polymorphism? I think I kind of got it. Who here feels like they understand universal quantification? Oh, you guys are going to make this easy. I don't need to teach you. Well, some of you didn't raise your hand, so not all. All right. So the talk doesn't actually start at RankNTypes. Got to step back a little bit. You will find out what the rank thing is. I promise that at least. So let's talk about a couple type signatures. So everybody here should be familiar with the identity function. Takes value, returns value. Does the identity function do anything with its value? No. Nah. So does it really matter what type that value is? Nah. So what can A in that first type signature be? Anything, right? Any of you that were here for Juliana's workshop yesterday have gone through this drill. Apologies. And then in the second type, we've got +1. The way we read that is that fat arrow there is a constraint, type class constraint. So what do we say? How do we put that in English? Well, A can be any type if A has a num instance, right? And then the last one is concrete. That's a concrete type, just one type. And in this case, we would say that the identity function in our num A is also polymorphic, just different kind. Different kind of polymorphism. So what's actually happening under the hood is when you're using Haskell anyway, it's actually putting the quantifier in for you by default. Because if you want to talk about the set of things that A could be, you have to kind of put that into words, right? So when we talk about universal quantification, we mean that we're saying for all A to A. That's the actual type of identity. It's just that we don't want to write a lot of these because we use type variables quite a bit in Haskell. A lot of polymorphism flying around. So the compiler just assumes whenever we introduce a type variable that we'd like to say for all, whatever letter or word it is. Now, because it's for all A to A, it could be any, right? And that's essentially what it's telling you. That it could be all A's in the universe. All possible types. And when we look at that syntax, just flip back and forth a little bit here real quick. You see that for all A dot? Has anybody seen dot syntax with lambdas before? Right? Ring a bell? So when we move from a simply typed to a polymorphic lambda calculus, because that's all Haskell is, just lambda calculus, right? We're essentially taking the same facility we have for introducing variables and binding them to something that we have in our functions, right? Because function takes arguments, they give names to those arguments, those are bindings. And then when the function is applied to something, that binding obtains a value. So if I have the identity function, lambda x to x, if I apply identity to the value 1, what is x bound to? 1, right? Similarly, we can concrete or bind a type variable. So this for all, you can think of it in your head as being kind of like a lambda that can be applied away, and then your x is now bound. But if your x is bound, if it's int, can it then become something else? No, because it's bound, it's stuck. Once you're bound, you're done. You're now an int. You can't become a string. So this assumption that the for all you want, that's prenex form. That's the name for it if you need to go look for it. All it means is that the for all bindings, the introduction of the type variables happens in the outermost leftmost position of the type signature. So outermost, leftmost, outermost, leftmost. So when we have the type of the const function, whenever you write that type above, GHC is just going to see that for all AB dot A to B to A. Some programming languages don't even do that. They actually make you write the for alls. But it turns out that these binders behave like curry functions too. The above is actually identical to the below. They say the same thing. It's really just the above is an abbreviation of the nested lambdas. Just like in Haskell, there actually are no multi-argument functions in Haskell technically, right? They're all just nested functions. It's no different with our type functions.
Good question.
Yes?
So you're saying that if you, in the first one, which is to say what happens if you define A to B to A in Haskell, if you partially apply on A, you get a polymorphic function, that is a function that is polymorphic in B. Or is it actually bound?
Polymorphic on, sorry?
So if you apply A
Yeah.
and to a function of type A to B to A, you actually get a value of type for all B to your bound A.
Yeah. So any unbound type variable, so if you apply your const A to B to A to a value int, and you haven't supplied some kind of witness for the type B yet, you're going to have, it's going to know what A is now, right? It knows A is an int. But it doesn't know what B is, so there's still going to be a for all B int, right? So that's actually the currying that I think Spiak was getting at, manifesting itself, right? And it's benefiting itself in our terms and in our types. And in fact, although this hadn't mattered until GC8, the order of your type binders actually matters now because of the type application feature, so FYI. But yeah, they're the same thing. And in fact, we can, if we want to pretend we're writing pure script for no reason at all, we can actually just turn on explicit for all, pragma, just like a little feature switch, and we can start writing our for alls and pretend we're writing a web browser app or something. Don't know why, but can. We're programmers, we like stating the obvious, right? That's all we do all day, explain the obvious to a computer. It should just already know the answer. All right, so let's look at something that kind of behooves us to want something different, okay? Something that seems like it should work, but at the moment it doesn't. So we're gonna try implementing this guy, right? So we've got a function argument. This is a higher order function, right? We're all comfortable with that in the immediate track. Who can tell me what A to A is going to be? Identity. Could it be anything else?
No.
Nah, it can't. And that's why I picked it. So you didn't think there was anything clever going on here. Can identity be applied to an int? Yeah. Can it be applied to a string? Yeah. So, who can tell me if that is going to type check or not?
It will not.
It will not. Because otherwise, why are you here? Why would it show you a bunch of things that work? Right? So what is it going to say? Couldn't match expected type string with actual type A. Okay, what's going on here? Right. We've bound A to int already by applying the function to the first value of the tuple. Not that the GC's type error here would really make that super obvious. I'll write a patch if you buy me a beer. So, it's not, but that should work, right? Doesn't it seem like it should work? Is there anything wrong with that code? Like just, ignore the types for a moment. You'll never hear that again from a Haskeller, but, ignore the types for a moment. It seems like it should work, right? So let's make it work. Do we have anybody that actually already knows this and came to the talk anyway? I saw a hand raised. And suddenly it works. It type checks. Ship it. It's done. Ignore the other bottom thing out there. Not important, right? Okay, so this is actually no longer prenex form, right? Because we've moved, this is not the outermost leftmost position. It looks leftmost, I know. But because it's in those parentheses, it's actually a rank 2 polymorphic type, that A. And it is now higher rank than rank 1, because that's what prenex form is, the default standard rank 1 polymorphism. So that's no longer prenex form, and whenever we want this kind of polymorphism, we have to ask for it. We have to tell it where we want our type binder in our type, because that actually means different things. And what we've done is we've essentially deferred the binding of A. See, previously it was trying to unify the fact that we were trying to bind A to int and string at the same time, right? By moving our type binder inside of the lambda, the function argument we had, we are essentially separating that unification so that A gets bound twice in 2 different call sites. Since they're no longer trying to unify with each other, they work fine. So if you like, you can think of higher rank polymorphism as a way of deferring binding and unification, kind of shoving it down.
Question?
Yes?
Does that mean the previous example of for all A, B, A was rank 1 and B was rank 2?
No, they're both in outermost leftmost position.
Okay.
This is not rank 1 because it's nested in a function argument.
Gotcha.
Yeah. So for example, if hypothetically I did that, it still wouldn't type check. Yeah.
But if you were being explicit, there is another for all outside in where you just pasted. Like if there was another problem.
Yeah, so you can mix rank 1 and rank 2 and rank 3 and rank 4 type variables. If hypothetically we had a B that didn't need to be rank 2, it could be in prenex form. So we could have one type binder in the outermost leftmost position. We could have one that's nested under a lambda. You can put them anywhere you want. And it'll still infer prenex form for anything you didn't specify. The only yes?
So I take this also as kind of a scoping thing, because as I read it, that A could not escape to one of the other arguments.
Yes, and in fact that's how we prevent people from seeing the ST and run ST. We're essentially hiding that type information so that you can't ever touch it, the mutable state.
That's scolonization, Chris.
Sorry?
That's scolonization. Because outside of the rank, basically conceptually outside of those parens, it's an existential now. It's not a universal anymore.
All right, so. Well, I'm not going to explain existential. Sorry, it's a black hole for type information. So to kind of touch on what he said a little bit here, when you use the identity function for a value, identity doesn't know what it is, but you do, right? So if you pass identity and int, the identity function doesn't know you gave it an int, and you know you're going to get an int out the other side, right? Existentials flip that around. Your code can know, in a sense, kind of a caller-callee dichotomy. You don't get that type information back out, but the code can vary its behavior. But I'm not going to cover that today. Well, actually, I am a little bit with this next function. A little bit, kind of. Okay, so we're going to go ahead and write this function. So what could num A be? Like +1, right? And if int and double both have an instance of num, then in principle they should both work, right? Because why would I show you something that just works out of the box? So apply f to I, f2, really it should be d. But names don't matter, right? Right? Right. All right. Same old type error, right? So we'll try to do the obvious thing here. Just put our type binder there. All right. That was supposed to compile. Fair enough. But if we actually do this. All right. So when we actually go to try to use it, we got a type error. We tried to use +1 on both sides of the tuple, even though one was an int, one was a double, and in principle this should still work. Can anyone tell me what the problem is?
Num is outside.
Yes. Our num constraint has to get moved under the binder. And in the actual code, the runtime representation, it's actually going to move the implementation of num with the value at the moment it is applied.
Why did that compile?
Because we didn't actually need the constraint yet. The type error happens at the time we go to apply, because that's when it actually needs the constraint.
So, like, in that case, A to A, there has to be an identity for it to work, right?
Yeah.
Because the A inside is not.
Yeah. Yeah, so if we don't actually use the constraint, we didn't properly move onto the binder, then it never needs it, and that actually works. So it's still type checking. This isn't runtime, right? Like, this is GCI, it's still performing type checking. I realize it looks like runtime because it's a REPL, but it's just that the blame for the fault moves to the. And remember I said about the dichotomy between like universal exponential, caller, callee? This is related to that. All right, so if we want to make our first example work, yes?
Is the num A shadowing the type variable inside of a for all?
Shadowing. Well, a better way to think about it would be to imagine two separate lambdas, just normal lambdas, and they both happen to have a binding of the name X. You just can't assume they're the same binding. They're just kind of like a separate independent binder.
And
So-
should you give it a warning for that?
At the type level,
If you have like a for all A implicit at the top, and then you have that for all A in the like identity function.
I think I see what you're saying now. I haven't tried shadowing for all binders.
I think that this is probably also a GHCI artifact, because if you tried to compile at both +1, you know, if you had that actually in your code there.
Yeah. Yeah, this is an artifact in the fact that like the way I'm using it has to get separately. Yeah, this would definitely get caught at compile time. It's just we're just moving the blame around. Okay, so we moved our num constraint under our binder, and now, so all right, everybody here understands the type class is unique. Unique pairings of type to instance, right? An int only has one instance of num. It's the proper way to do type classes. If somebody tells you otherwise, it's nuts. All right, so because of that, normally, you can actually just inline the code from an instance of a type class to its call site, right? Because normally you know, like, okay, this is an int, I'll just copy and paste this code. I mean, really, like, a compiler is like a very junior programmer with a lot of energy drinks. Who's got to copy and paste some code around, right? But it actually can't do that here. It has to actually move the instance, almost like an O-style V table, to the data. And the mountain has to go to Muhammad when you have a type that's quantified like this. If you ever use an extensionally quantified type that has a constraint in a data type, same deal. Mountain goes to Muhammad, and then you're going to just be carrying around your code with your data. So, there's a tension here. We saw code that in principle should have worked, but the type system didn't permit us to express. What I like about RankNTypes is that it opens up the space of things we can express, and it costs us almost nothing. Maybe performance. The Mountain Muhammad thing can cost you some performance, right? But in correctness, it costs you nothing. And in fact, it actually lets you prevent some things you might not want. And not only lets you express things you want, but it actually gives you opportunities to prevent things you don't want. So this is a lot of PL design, right? When you're trying to design a programming language, you want to make everything expressible in the programming language in terms of the types to be something that makes sense. You don't want programmers to be able to express something that doesn't make sense. But you don't want to prevent them expressing something that does make sense, right? And there's a little bit of a tension there.
Question.
Yes?
Does it cost anything in inference?
Yes. Good question. All right, so rank 2 polymorphic types are generally inferable. Rank 3 and up are generally not. So I think, and I could be wrong about this, I think JC has best effort inference for rank 2, rank 3 and up. So the ranks are just the nesting of, like, if you have like a function that's an argument to a function that is an argument to a function. If you have a for all binder all the way down that hierarchy, that's a rank 3 because it's 2 layers down. So it can't infer that, but it can infer with a rank 2. But it doesn't matter in practice because you have to write the type signature to ask for the higher rank type anyway. And that, whenever you specify your higher rank types, everything else becomes decidable anyway. So you just never have to worry about it in practice. It's not like GDTs where like your type inverse could like get kind of wiggy, kind of like Idris, where it's like, well, we'll do our best, but you know, that kind of thing. It's not like that. It doesn't really cost you inference.
I thought the reason they said rank 2 and rank n was the inference. So why
Yeah,
do we
but
need
people
rank
just started defaulting to using rank n unless they wanted to specify that they're trying to stay in a strictly inferable segment of Haskell. So if you look at like the lens module, like Recommit puts rank 2 types above everything because he uses them for the type synonyms. It's not because he needs like specifically the rank 2 pragma instead of the rank n. It's because he's trying to communicate, I'd really like to keep this inferable, so don't add anything higher rank than this. It's just documentation. Yes?
I was pretty sure that systemF, even with rank 2 types, not general rank n, but rank 2 was still not, still did not have most general unifications.
It's
so
you're talking about a
even
different
rank
problem.
2.
You're talking about a different problem. All right, so this is a bad type system, right? Pardon me the Venn diagram. I basically screenshot this out of our book. So you know, one circle is programs that work. One circle is programs that type check. So there's a lot of programs that type check that don't work, and there's a lot of programs that should work but don't type check anyway. So this is terrible. You don't want this. You don't want a programming language like this. What we want is something more like that, where we have this nice intersection of things that work, things that type check, and the stuff that is in those 2 other bad spaces are much smaller. So, higher rank polymorphism gives us a win on both ends of that spectrum. You already saw an example of where let's express something in principle should work fine, right? So it's opening up the space of programs that work and moves them into things that type check, where previously they did not. So here's the example from Lens. This one's using the rank 2 type pragma instead of the rank n. It doesn't really change anything. I mean, obviously it limits you to rank 2 instead of rank 3, 4, 5. And the only reason for the way this type signature works is he's trying to make certain that if you use the lens type synonym in a type, it's so that if you don't have this there, you can't use the lens with 2 different functors. You can't, in essence, you won't be able to use the lens more than once, right, in the same function.
Why is it that rank 1? Because isn't that prenex right there?
No, because I didn't explain this for type signatures. So prenex for a type signature would be that would be prenex, right? But he's moving it under the equals, and that is essentially deferring the binding of F. So you can use the same lines more than once with different functors. You also notice that it actually moved the functor out of the arguments of the lens type synonym. You don't have to mention F now. Why bother? They're not going to instantiate the same thing anyway. So, in essence, it's let us not talk about something that can vary.
Question.
Yes?
Why rank 2? Why not rank n in the previous slide?
Well, so we can infer rank 2 types. It doesn't mess up our inference. Rank n could. So again, there's really not much difference between the pragmas. It's just that rank n will let you do rank 3 and up. Every commit tries to write his library so that everything stays inferable because he likes to be able to kind of have a conversation with his REPL, you know, be like, you know, put some code together that type checks and just kind of ask the REPL to type, right? You want to have that kind of bidirectional conversation with your compiler. If you break inference, you lose a lot of that, right? So again, it doesn't really matter that much that you use that specific pragma. It's just a way to signal, hey, this is what I intend, right? It's just a signaling of intent.
Could you explain the using the function twice
Yeah, sure. So when we look at this example right here, we've got an A to A function that uses a numbsys, right? We applied f to two different values with two different types and two different numbsyses, right? So when I said, use the lens more than once, what I was trying to say is that, again, just like this situation, in principle, you could use a lens with more than one functor. There's different kinds of structures you can use a lens with, right? If he had not written the type synonym with that higher rank type for the functor, it would have made it so that you would have like lens FSTAB, and then the first time you use lens, you're going to bind it to the first functor, and then it's stuck, right? It's now bound to whatever concrete type you use it with, a list or whatever lens functorial structure you're working over, right? But in principle, that should work fine, because lenses are made to work over different kinds of structures that have a functor, right? So the higher rank type variable, allows you to use it multiple times within a single function. Especially, this comes up when you're parameterizing the lens you're using. This doesn't come up and you just kind of use it, but it's not an argument of your function, because it's the fact that you're mentioning it in your types. If you don't parameterize it, and it's not mentioned in your types, then it actually gets unified separately anyway. So an example of that would be something like this. What did I do wrong? All right, I didn't finish there we go. Thank you. All right, so this one works fine without any high rank polymorphism because we didn't parameterize the function. We don't mention the type in our types integer. So Haskell can actually instantiate the A for our two uses of the identity function here separately, and there's no problem. It's when we parameterize things that this becomes a problem. I think that's one thing that people have a hard time with high rank polymorphism is they think, oh, that works fine, I do it all the time. Not if you parameterize it. You lift it out as an argument, you're trying to talk about the type, then it becomes a problem. We've got a little bit of time, maybe a minute or two. So I'm going to skip the other file. Actually, here, I'll show you real quick. All right, so F1 is in prenex form. G1 is in prenex form. That's what it looks like if you have a constraint. The type binder goes before the constraint. So F1 and G1, rank 1. F2 and G2 are both rank 2. The difference is that one is moving the constraint under the rank 2 binders. Then F3 is a rank 3 type. So you need more than the rank 2 types pragma for that one. You're going to need RankNTypes. And it's rank 3 because it's a function argument that is an argument to a function, which is an argument to a function. So 2 layers deep, rank 3. All right, I'll leave it at that so in case anybody has questions. Anybody? I hope that means I did really well.